Hey, APCal class, we're going to keep going through the 4.2 notes, and where I left off we were talking a little bit about right side, left side endpoint rectangles, and one of them is producing, in this case, a lower sum, an underestimate for the area under the curve, and then in this case it was the left side rectangles that produced the upper sum or the overestimate. And again, this is going to be dependent on whether or not the function is increasing or decreasing. On this decreasing function, it turns out that the left side rectangles will produce that overestimate or upper sum. Now, as we were going through this, an important factor of this is calculating the width of the rectangles that you're going to draw in there. Now, in the directions, they did tell us that we were going to use five subintervals. And so if we're using 5 subintervals, there's a pretty simple formula for calculating the width. If the interval that we're working on is from 0 to 2, and that would be from A to B is what we would call that, that B minus A over N is how we can always calculate the width of the rectangles that we want. And that's really important, is that width, that B minus A over N. And so 2 minus 0 over 5, since there were 5 subintervals, our width was 2/5, okay? So I could count that out: 2/5, 4/5, 6/5, 8/5, and 10/5, which ends at 2. So that works out the way that it should. Now, we went through and we calculated those estimates using the right and the left side endpoint rectangles. What I want to add to this now a little bit, because we're going to use some of this sigma notation, and so we have to implement, when we do the areas of these rectangles, it's width times height or length. But what we did here was we didn't really use the sigma notation. We just physically went in and just added up, because there were just 5 different rectangles to add together. And that, for the most part on the AP exam, this is practically what you do. There may be, I do need to introduce the sigma notation as well and just share that with you, because they are starting to just add a couple questions about that. And it is fairly complicated, but I want you to just try to follow me with this. So because the width is 2/5, now the height is determined by the function value. In other words, the curve, here has all these different y coordinates along it. And so to get like a particular height, in this case the height of this first rectangle, is going to be found by taking f of 2/5, right? So if I were to plug 2/5 into this function, there would be a certain y coordinate right there, right? And that's actually where I'm calculating the height of this first rectangle. Now the I that goes after that just refers to it's like the counter in the number of terms. If this is the first rectangle, then I would have 1 in there for the I. This is my first rectangle. So f of 2/5 times 1. So that I just means, which rectangle am I on? If I'm on the first one, then I'm doing f of 2/5, and that gives me that height. If I'm doing the second rectangle, then I put a 2 in there for I, so I'm doing f of 4/5, which is going to be right in this corner here, and so on. If I do in the third rectangle, I is 3, and that's how I'm getting that. Okay, so that's why there's the I involved there. That just tells you which rectangle am I on. Right? Now over here on the left side endpoint rectangles, the formula is just slightly more complicated, because you have to, if we're starting on the left side, we actually start with, technically, we're going to be doing 0, for that first input value into our function, because f of 0 is actually this first height. So instead of just having 2/5 I, or f of 2/5 I, it's f of 2/5 I minus 1, because when I'm doing the first rectangle, I'm actually want to be taking technically f of 0. So when I put in my 1 in there for my first rectangle for I have to go 1 minus 1 to get 0, and 2/5 times that is also 0. So I'd get f of 0 for this first, height of this first rectangle, which is what it is. The actual height is 5 on that first rectangle. And so that's why this is set up as I minus 1, because we're actually, it's the first rectangle, but we have to go backwards 1 to calculate that first height. Okay, and then on my second rectangle, that height is calculated right here at 2/5, and so when I put 2 in there, 2 minus 1 is 1 times 2/5, and that's why that one ends up, where it does. So the left side endpoint rectangles are a little bit, the formula when we start doing the sigma notation is a little trickier, because you have the I minus 1 in there. Okay, so if I were to go down here and write this out in sigma notation, here's how this would look with this sigma notation. So remember, it's the sum of, and then you start, first to last term. We're going from 1 to 5 since there's 5 rectangles in there. And then the 2/5 is that constant width, okay? So it's width of 2/5 times height, which is f of the 2/5, and then times whichever, 2/5 times 1, 2/5 times 2, and so on to get each of those, function values that give me the height, okay? So this is width, this 2/5 is width, and the f of those, different spots are giving me the heights, and then the e here, this sigma, means to add all those together. Now what we do when we calculate this constant, which is the width, gets pulled out in front of your sigma notation, okay? Now here, what I'm actually doing is plugging it into the function that we have, okay? Because it was negative x squared plus 5, then I'm replacing the x with the 2/5 I, right? Because it's f of 2/5 I. So that's why I have negative 2/5 I quantity squared plus 5, okay? So this would be my actual sigma notation. Now there's a button on your calculator that does this, so once you get this, kind of figured out and set up, then you can enter that into your calculator to come up with this. Now we did it physically by hand, which is mostly what you're going to do, but just to show you the comparison of the two, you can do it on your calculator. I'll just show you. So if you hit the math button right there, in option 0 on mine anyway, you'll see there should be a sigma in there, and then you can just pull that up. Now I already did it just to save time. So, and I actually put in the 2/5 out in front, which is 0.4, and then you just type in your lower and your upper bound, and then it was negative 2/5 I squared plus 5, and instead of an I, you just use your x, okay? And hit enter, and it gives you that 6.48 value, okay? So, and then in a similar way, and then this is where it would get more complicated because you have to do f of, 2/5 I minus 1, and then that has to get plugged into your function, the 2/5 I minus 1. I went and simplified that just a little bit. I distributed the 2/5 through and actually just put it as a common denominator. But, so you could do that in the same way and type that in your calculator. Now we did that here with the actual just values that, individually, since there was just 5 of them. But you can use the, the summation function on your calculator to do that as well. It'll give you that same value, okay? So that's left and right side endpoint rectangles, okay? We know that one gives us an upper sum or an overestimate, one gives us a lower sum or an underestimate. Okay, now there's another way that we can use these rectangles to calculate an approximation, and that's called the midpoint formula, midpoint rule formula. Okay, so it says in the previous example, and it actually is supposed to say example 4, we could say that the area we computed using the right side endpoints was the lower sum because it produced an area that's less than the actual area under the curve. Likewise, the area that we computed using the left side endpoints could be called the upper sum because it produced an area that's greater than the actual area, so that was an overestimate. So don't assume that right side endpoints always produce a lower sum. And again, it depends on whether the function's increasing or decreasing. So that's what we're seeing here. Okay, so now this midpoint rule. Okay, so using that same negative x squared plus 5, which is just that parabola that opens downward like that, on the same interval from 0 to 2 and 5 subintervals, we're gonna use this midpoint rule formula, and it looks really complicated, but basically all that it's saying, and it does look really kind of nasty, but okay, so this b minus a over n, again, that's the width, right? This is our width right here. Get my pen up. Right here, this is width, and then f of some big mess right in here, that's the height of the rectangle, okay? Now let's try to interpret that big mess that we have. Okay, so it says b minus a over ni plus b minus a over n I minus 1 divided by 2. You're adding two things and you're dividing by 2, which really means the average of two things. We're averaging our two x coordinates, okay, the two endpoints, so in other words, right? So if these are counting by 2/5, right? So this is 2/5 and 4/5 and so on like that, okay? So what we're actually doing is we're saying, okay, well, if I start at my first one and then my second one, or this is the previous one actually, this is the first one and this is the one before it, I want to add those two x coordinates up and divide them by 2 and then find the function value right in between them. So I'm actually finding, it'd be adding 0 and 2/5 and dividing them by 2, and then I'd be actually right in the middle there at 1/5. And that is actually, if I make this a little bigger here, that's where I want to calculate my height. So when I draw these rectangles, I want to make the height of my rectangle as high as right to that middle, middle of those two, it's right in the middle of the rectangle is where it connects with the curve. And so that's the way I tried to draw them was so the middle of the rectangle connects, with the actual curve. And so that's going to happen right in between each of these. So that would be at 1/5, and then in between 2/5 and 4/5, that would be at 3/5. And in between here, this would be at 5/5 or at 1. In between these two, so that'd be 7/5 in the middle there, and in between here, this would be 9/5. Okay, so that's really what that midpoint formula is telling us to do. It's saying just average, this x-coordinate and this x-coordinate, and then just go in the middle and then find the height right in the middle and use that one. Okay, so a simpler way of writing that right here, they're just saying add the first x-coordinate and then the one before that, add those together and divide by 2. So this one, 2/5, 0, add those up, divide by 2. Then here, 4/5 plus 2/5 divided by 2, that would be 3/5. That's what that's telling us to do. Okay, and then times delta x. Delta x means the same as this. It just means what's my change in x, or the width of each of these rectangles. So delta x eventually is going to replace our b minus a over n. It kind of means the same thing. It means like, oh, what's the amount that we're moving, horizontally? What's the width of those rectangles? Okay, so with that in mind, let's go ahead and see if we can calculate this. So now what we want to use, so since we're working with this function, f of x is equal to negative x squared plus 5, okay, and we know that we have n equals 5, so, and then from 0 to 2, that's all of our important information that we have in there. So we know that our width, again, is going to be 2/5, so when we do our area here, now we're just going to do these, we're not going to do it with the sigma notation, we're just going to do this physically, just the 5 numbers, we're going to add them up like what we did, up here in these examples here. We're just going to grab the correct function values there. Okay, so what we would have is, now according to this, we want to do our b minus a over n, so we're going to do that, which is still width of 2/5, okay, and then we're going to go f of these middle values, because I'm adding up 0 plus 2/5 divided by 2, that's right in the middle at 1/5. So I want to do height at 1/5, which is in the middle of that rectangle. And then I want to do the height at 3/5, which is in the middle of the second rectangle, right? 3/5 is the middle right there of that second rectangle. And then f of 5/5 in the middle of the third rectangle, f of 7/5, which is in the middle of the fourth rectangle, and f of 9/5, which is in the middle of the fifth rectangle. Okay, so I hope that makes sense. I have them marked here, okay, and we're finding the heights of each of those, right? So we'd be plugging 1/5 into our equation, negative x squared plus 5, and you can use your calculator to do that. If I put in 1/5 into that equation, or a 0.2 in there, I end up getting like 4.96 for that, and this is all going to be calculator work. If I plug 3/5 or 0.6 into that equation, I get 4.64. Okay, if I plug in 5/5 or 1 into that equation, I just get 4 for that. If I plug in 7/5, I get 3.04. And if I plug in 9/5, I get 1.76. Okay, so if I add all of those 5 numbers together and then multiply by 2/5 or by 0.4, it turns out to be 7.36. Okay, now it's important to note that this, using these midpoint rectangles is a better estimate than either the left or the right side rectangles, because we can see we get a value that's between these two, and we know that this was an underestimate and this was an overestimate, so a number that's between these two definitely has to be the best estimate of the 3. And you can kind of see it makes sense, because on these rectangles we have a little bit of the rectangle that's higher than the curve and a little bit that's lower, and so it would make sense that it's kind of balancing out a little bit. Still, it's not exact, but it's pretty close. Okay, so that is what a midpoint sum is. That's how you do it. You find the middle of each of those rectangles and then find the function values for the heights and add those up, multiply it by the width. The width, again, is always going to be that b minus a over n. In this case, 2 minus 0 divided by 5. Okay? Okay, I think this will be the last one that I do in this video, and then we'll finish up the last examples in the last video. So here it says, using the midpoint rule, approximate the area under that curve and above the x-axis and on that interval from 2 to 6 this time, and using 4 rectangles of equal width. Okay, so I'm going to write down the important information. So my function that I'm working with is this rational function 8 over x squared plus 1. I'm using four rectangles, so n is 4, and then my interval is from 2 to 6. So I want to use my formula, that for width, I want to say, okay, my width, my formula for that is b minus a over n. And so I'm going to take 6 minus 2, that's b minus a, and n is 4. So that ends up being 4 over 4. My width for each rectangle is 1, okay? So I've got 4 rectangles in here, and you can kind of see it, 1, 2, 3, and 4, okay? And my heights on these now, heights are going to be the function values, right? So we're going to do this in a similar way to the previous example. We're not going to use the sigma notation on this one. We're just going to do our 4 rectangles and get those function values. We just need to make sure that we input the correct x-coordinate for each of those function values, because we want the middle ones, right? So if I look at what I have right here, we're just counting by, this is 1, 2, 3, 4, 5, and 6. So we're just counting by ones there. But what I want to do, remember, I'm going to make this a little bigger. So the rectangles that I'm interested in, they're going to intersect the curve right in between these points here, right? And since my widths are just ones, I'm counting by ones, but I don't start until I get to 2 in this case, because that's the area that's shaded here. I'm not starting until 2. Okay, so right in the middle, basically in the middle right there, so I would draw my rectangle just to get a visual on this. So this is the rectangle that I'm using for the first one. The next one intersect right here. So if I take that straight across, you can see that, on the left side of the rectangle, it's kind of it's an underestimate, but on the right side, it's an overestimate, right? So it kind of balances out a little bit that way. Okay, right in the middle right here. The right side's a little above, the left side's a little bit below. So we get that, and finally this last one. It's getting pretty flat here toward the right end, so these rectangles actually look pretty close to the curve then. Okay, so those are my rectangles I'm actually going to calculate the areas of and total them up. And that's what's going to approximate my actual area of that gray shaded part. Okay, so what I'm going to do now to get my area, so area, let me go back here. So area is going to equal now my width, right? So it's always the width, and I found the width to be 1, right? And my height is going to be the f of each of these. Now think about where I intersected these, right? This intersected right here between 2 and 3, which would be 2.5, and I'll say 5 halves, right? That's right in between. Right in between 3 and 4, that's gonna be 7 halves, right? 3.5. This is 4.5. That's 9 halves. And right here, that's gonna be 5.5, which is 11 halves. So that's what I'm inputting. I'm gonna do f of 5 halves for my height. I'm gonna do f of 7 halves, f of 9 halves, f of 11 halves. Those are the heights of each of those rectangles. Okay, the widths are always 1. Okay, so I'm going to say my width is always 1, but now I have to do f of, and like we said, the first one is right here at 5 halves, f of 5 halves, plus f of 7 halves, plus f of 9 halves, and only 4 rectangles this time, f of 11 halves. Okay, so that's what I'm totaling. And again, so let me just show you real quick on the calculator how we can do this. We have 8 over x squared plus 1. Okay, so if I'm going to enter that, excuse me, so I'm going to clear out this other function. I've got 8 divided by, in parentheses, I've got x squared plus 1. So that's my, oops, I didn't get my plus in there. X squared plus, come on, plus, there we go. X squared plus 1. Let me just take a look to see if that looks kind of like what we have. Okay. Yeah, and we were just looking at the portion of it. If I change my window, I'm just going to go from, I'll go from 0 to, I think they had 7 on there. Clear that, 7. Look at that. And we can probably condense the height down. Yeah, it's fine. This is approximately, I guess, what we're looking at. Okay, So let me go back. Okay, so I've got that in there in my y1. Okay, so when I do these function values, a quick way again is to use that alpha F4 button, and then you just choose your y1, okay, and then I can add, okay, so I can do alpha F4 of, and then I'm putting in 5 halves, which would be 2.5, right, plus alpha F4, okay, y1, and the next one that I was doing was 3.5, plus, and then I can do alpha F4, okay, y1, oops, y1, and the next one was 4.5, so type in 4.5, and then I'm going to go, I need to get up to what, yeah, 5.5 is my last one, okay. So one more time, plus alpha F4 y1 of 5.5. So that was the, those were the middles of each of those rectangles. So this is probably the, if you enter that equation into your y1, then you don't have to always plug these in. You just put them right in there in your calculator, hit enter, and we get approximately 2.3396. So I guess we could go 2.340, but we should go, you can either, they say, on the AP exam, you can either truncate, which means just stop right there, or you can round. I would just truncate, then you have to worry about rounding. So 2.339, go 3 decimal places on that, okay? 2.339 for that area. So A equals 2.339. That's square units, that's an approximation for area, but it doesn't give us units, we don't really have to label anything. Okay, so that's a real quick example of using the midpoint rule to approximate that area. And typically, like I say, on the AP exam, you'll just be using this, but I am going to show you some of this sigma notation that we're going to introduce, with the eyes and the counters a little bit. Especially in the last video, we have to do it just a little bit more. But I'm going to stop here for this video, and we'll finish up the last 3 examples.